remember hearing my physics professor, one of them in high school, in graduate school, talking about how the textbooks we use were slightly lower than what the freshman textbooks were in the Soviet.
Trying to, make you feel like a jerk.
Yeah. Well, and it's the truth, but it's for different reasons. It's the same reason that the best university is considered the best tech university in the world is in India. You take almost 1 billion population, weed out just that, and just by the numbers alone.
Yeah.
It's a highly competitive marketplace for academics. Okay, so let's go to the diverging mirrors. And these are, like I said, there's only one type, but they're tricky to look at. And a lot of the stuff I'm trying to lay out now will be directly translated to how we deal with lenses. Now with diverging mirrors, now we got this job here. Now here's the thing, the reflecting surface is on the outside, but the radius of curvature is on the inside. It's a negative radius of curvature, and it's a negative focal point. Because light diverges as though it came from inside the mirror. So, when we played the same games for ray tracing, now we have to deal with a slightly more sophisticated analysis, but at the same time, there's only one analysis. So we put an object over here, and it doesn't matter where we put it. So remember the criteria, are you inside or outside of R, inside or outside of the focal point for a converging mirror? You can only get to one side of this focal point. There's no other place to be. Unless you could take a lens and project an image that would otherwise converge over here, but it never gets there because it reflects off. I mean, there is a way to make it happen, but it's very, very, not complicated. It's just a much deeper process. But for all practical purposes, we can't get objects inside that mirror. So, again, we play the same game, right? Parallel principal ray. Now, normally it would come in here, but it can't. Kind of like your wallet that would want to give you a hug because you switched to Geico. It can't. It's a wallet. It doesn't have arms. Commercial on the radio. It's just
I really haven't, but sounds
no,
like
it's just on the radio. I don't watch TV. I only get talk show radio. And so I get these silly commercials like that. Okay, so I like the lizard one there. I like the guy. I just don't translate it on the radio.
I like the caveman.
Okay, so now what's the second principal ray? Through the focal point, right? Problem is, to get to the focal point, probably going to do something like that if it could continue on. But once it gets here, it's going to come out this way. And the third ray, actually, we could do any number of rays here. We could either go, we could take the easy route, the cop out, if you will, and just run one to the origin. It's angle of incidence, angle of reflection. Or we could try to get one to the radius. And the one through the radius is going to come right back out. Yep.
You're through the focal point one that didn't make it to the focal point. That is parallel to the axis.
Always.
Yeah.
Always. So I'm going to use this one because it's just too hard in a diagram for me to squeeze that other one in there. So the ray coming in this way is going to come out this way. And maybe in another color I can just sort of point out the third one would be this one. Now, here's the thing. Light's doing this, but to our mind's eye, we trace it back to a single point of origin. and that point of origin would be defined by this ray, which, by the way, limits the size. The image will be in here no matter what, by this triangle. Then the light coming out, we can trace that back this way. You can already see the green converges there. And is there one more? And this one, if I were to trace this back, it's amazing how all my drawings today are just coming out perfectly scaled. It's beautiful, man. So my image would be right there. So I drew 4 rays in here, but parallel to the focal point and to the origin are probably the easiest ones to look at for this particular situation. 4 principal rays, you only need 2, but 3 is usually more reliable. Okay, so now let's do the calculation. If F happened to be 10, we would say F was negative 10 centimeters for radius of curvature in the virtual direction. We would have an object located at a distance of, just to be similar to what we had before, how about we make this 30 centimeters positive, as it's in the real space. So if we're going to find the image, to get I, we would say I is related to 1 over the inverse of negative 10 minus 1 over the inverse of 30. So because these are additive, you're going to get a larger number here, therefore a smaller number for I. Because you're not taking a difference because of this minus and minus 1. So that would be 3 30s. This would be negative 30 over 4.
Negative 7.5.
So it should be close to F, close to negative 10, but a little bit less. And a little more than 7, a little less than 8. That's how you deal with the diverging here. Now I can do 15 examples of this, but just note, wherever I take this object and put it in here, this line never changes. You see that? Because it's parallel. If I bring it, however I bring this in, I'm always going to be limited by this ray, which means that the intersection will always be inside of it. In fact, this one, if I drew it carefully, it's supposed to be on that line. Look at that. Here I am bragging about my accuracy, and it isn't. There we go. Look at that. Perfect. So, makes life for an easy calculation. Even though conceptually it's not as easy to do. So, any questions on how these work? Keep in mind 2 things. First of all, you can physically have a negative object distance. All you have to do is have something that moves on.
Say that again?
You can have a negative object distance. Right? You can take a lens or a mirror or something and project what would be an image back here. Put the mirror in place, and that light will be diverged, will be ultimately redirected as though it came from back here, coming outward. Reflecting off this image doesn't make any damn sense because you physically do it. You play with optics in a lot of different ways. And you see it with light and a mirror or lenses. Okay, so let's extend this now to lenses. And there are a couple of distinctions that are very important. By the way, I don't know if this was talked about. How many different ways, when light comes in and is incident on a surface, solid or liquid, but let's just say a solid surface, how many different things can possibly happen? Let's not limit our brains to what can happen here. So you got light coming in and you got some surface. What can happen to that light? Reflect off. pass through. As it passes through, depending on the nature of the material, it can be bent. Call that refracted. It's transmitted because it's going through the material, but it will be bent in some ways, at least as it appears. A couple other possibilities. It can be absorbed. It can be absorbed on the surface. If it's absorbed, then it can do one of two things. You can either get absorbed by electrons, re-emitted. Fluorescence is an example of that. The way mercury works, mercury fluorescent lamps work, you got a mercury light source inside that produces a huge amount of ultraviolet light. That ultraviolet light then gets absorbed by this white surface. But the white surface is basically a bunch of different pigments that are ultimately absorbing the ultraviolet. They're not absorbing visible light, they're absorbing ultraviolet and then emitting visible light. So they can be absorbed by electrons and then re-transmitted. Or it can just be absorbed thermally as heat. So there are 4 possibilities at least that can happen. Well, there's a 5th too. This guy won a Nobel Prize for it. It's absorbed by an electron. If it's more than the energy necessary to excite it, you can even kick an electron off. Call that the photoelectric effect. So one possibility, you can just kick an electron off, or you can excite an electron, or you can generate heat. I'm going to call that more. Okay, so there's all kinds of possibilities. So these are just 2 possibilities that we're dealing with. And ultimately, by the way, they all involve the same thing, whether it's obvious or not. Energy being absorbed and somehow responded to by electrons. Everything. That's more of a 213 concept. We'll get to it. It's energy absorbed by electrons. Either those electrons spit it back out forward, excite, release, spit something completely different out. All are possible. But it's only just an electron doing something to a photon of energy, if you will. It's kind of funny, all these possibilities, and they all shrink down to something very simple. Okay, so we're going to change this now to mirrors. Or to lenses, excuse me. And I'm going to treat only thin lenses because there's enough application for thin lenses we don't have to go any deeper than this. So the idea behind thin lenses is that, here's my lens. Here's my optical axis. Here's my center point. And the idea behind a lens is that light coming in physically transmits through the lens. But as it transmits, it gets bent inside the material because of the index of refraction. We call it the optical properties of the lens. And then ultimately redirected back outward. Passes through and comes out the other side. So it's a dual sort of redirection process, one at each interface of the lens substance. Now, to this end, if you take parallel light coming in, parallel light will be redirected for some lenses to a physical point. This is the shining
magnifying glass.
It's the magnifying image where you take an object from a lot far, far away and concentrate that light to a single point, or nearly a single point, and that point is what we call the focal length. This is a converging lens. So the rays converge to this type of lens. And by converging now, it doesn't mean they reflect converging, or they converge on this side. They converge after they pass through, because that's what lenses do. They allow transmission. It's not a reflection process. It's now a transmission process. So when they converge on this side. Now, the other possibility is there are lenses that when you shine parallel light, they diverge based on their geometries, their surface geometry. But they diverge as though, kind of like with a diverging mirror, as though they come from a physical point of origin. So we got one issue here. First of all, where is an image formed from a converging lens compared to a converging mirror? First of all, when you look at an image through a lens, what is sort of the assumption?
It's behind the lens.
Well, the assumption is you're looking through it, right? You're getting light that's passing through it. One way or the other, it's light passing through the lens. You've got to pass through the lens, otherwise you're not looking at the lens, you're just looking at the light. Right? So the idea is that you're observing something, or the light from something, passing through a material. Which means if we sort of define this side as the observer side, I'm going to call this the observer space. Light coming through forms an image we would see over here. This is the observer space. This over here I'm going to call, conversely, the object space. Okay. Now this is important. If the observer is on this side, put an eyeball here. This is Russ on a Saturday night. He's got a little bit of bloodshot in there.
Okay. This is me at work.
Okay, so when you're looking at this from the transmission side, if you will, light coming out of the lens, the question is, for the light that passes through this lens, where does it end up? Where does the effective point of origin look like to the observer? Everything is always about the observer. So, two distinctions now. When you have a lens, you don't have just one focal point. You have two focal points.
One on either side.
One on either side. So that's one distinction. So if this is F, I'm going to call this F prime. Same physical distance. If this is F, then on the other side in the observer space, this would be F prime. Now I need these because I need to be able to use these to trace the rays produced for a given object to see where the image ends up. Let's get rid of these for now. Let's look at what happens when you take an object and look at it. Put an object over here. So if this is an object, the distance from here to here is the O distance. I'll draw that there so we get too much. The ray trace, find where the image ought to be formed. Start by drawing a parallel line. Well, we know by definition for a converging ray, that's what we get. Now, this is probably something Sam talked about this too, didn't he? The next ray, so that would be ray 1. It goes straight through F. The second ray goes through F prime. Pick any other ray. The ray that goes through F prime comes out parallel. So there's one little distinction between a lens and and a mirror is that you use opposing focal points, f and f prime. Parallel passes through f. Light passing through f prime comes out parallel. And then an easy third reference line is a ray that passes through the center of the lens. And it just keeps on going. Just like that.
Perfect again.
I remember my physics instructors would always have like the big ruler and all that. So again, you do get a convergence. Over here is where your image is formed. To calculate where an image is, you use the same image formation relationship. So it's accurate for both objects, or for both mirrors and for lenses. The idea is wherever the object is, you take the inverse of the object distance from the lens. Now, by the way, this assumes opposite sides to the observer. Object space, even if the object doesn't physically exist there, is opposite to the observer. So if O is positive, and I'm looking from this direction, it implies that the object is on the opposite side of the lens. Now, hypothetically, O could be negative if I have a second mirror or a second lens reflecting to produce an image that would in fact be behind the lens, even though it doesn't necessarily get there. It's a different issue for a different day, but it can happen. So O is positive when it's on opposite side of the observer. I is positive when it's on the observer's side. Because you want the image physically where the object can be seen, or where the observer is looking. What's ironic about this, when you wear glasses, you never see a real image. You never see an object or an image on the side of the lens where it's being, where your eye is. It's always on the opposite side. Okay, now what this means then, for practical purposes, if we look at our ray diagram, it means that in object space, O is positive in this direction. In observer space, I is positive in the opposite direction. So it's exactly backwards from mirrors in that respect. But the importance is, the reason this is positive image space, the positive image values here, is that if you have an image formed on this side, you can put a piece of paper there and physically see it. If you're looking at an image, at an object, and the image appears to be out here, you can't put a piece of paper over here and see it. Because what you're physically looking at from your mind's eye is light passing through, not light sitting over here, because it's not a mirror. It doesn't reflect backward. Okay? Obvious, but not so obvious. Magnification works the same way. So, as far as calculations go, then those are really the criteria to deal with. So, as an example, if you had a lens with a focal length of, say, plus 10 centimeters. And by the way, plus 10 centimeters is another way of saying plus 0.1 meters. How many of you have glasses or have ever worn glasses? Almost everybody? Not everybody, but almost everybody? Except for us. Did you wear glasses? No? I mean, I have sunglasses. Incidentally, 1 over f for this lens would be 10. Inverse meters. That would be the prescription. If this were a pair of eyeglasses, and this was the lens on a pair of eyeglasses, this would be a plus 10 diopter lens. So for those of you who had glasses, you get to a little prescription. it's actually measuring in inverse meters. This is called the diopter unit. So there's a lot of cool things related to just physics of the eye, and it's based on the inverse of f. The reason it's based on the inverse of f, which is kind of cool, it's because we always do our calculations. 1 over I O plus 1 over I equals 1 over f. Well, if you're an optometrist sitting in a chair, it's a lot easier just to deal with 1 over f and 1 over I and 1 over f. It's a heck of a lot easier just in dealing with basic numbers. Plus, the smaller the focal length, the stronger the lens. The smaller the focal length, the more the lens bends. The greater the 1 over f. So as 1 over f is larger, the stronger the eyeglasses. So again, it's a nice number to use because when you have bad eyesight, you need a stronger lens with a higher value. So we sometimes call this 1 over f optical power.
So the shape of a converging lens, earlier you were talking about, I guess, the mirror on Hubble and saying parabolic as opposed to spherical. On these lenses,
spherical or toroidal?
Spherical or
toroidal.
I don't know what toroidal means.
If you have astigmatism, it means that you have a different focal length on 2 different axes. So you have a radius of curvature for each axis, so that you warp the light that you see. Yeah.
So
it's like a football shape,
but if you
as
have
opposed to a circular spherical shape.
I mean, if you have a spherical side to your lens, then I'd imagine that the focal distance is still going to be 1/2 that radius. But if you have,
they don't have to be the same.
Well, I'm not saying both sides are the same, because on a pair of glasses, obviously they're not. But since you have a focal distance on either side, right? Is there a relationship you can draw, like you do with the spherical mirror, between the focal distance and the radius of one of the sides, or do you have to consider both of the sides?
Yes, you have to consider both of the sides. 1 over f looks like the index of refraction minus 1. N will always be greater than or equal to 1. The greater n, the stronger the optical properties of the material that are producing the lens. There are, for people that have really, really bad eyesight, might be somebody with a +10 prescription, you would use a material that is a very high index of refraction so that you don't have to have such a thick lens.
Yeah.
Okay? And then it's related to 1 over the radius on one side minus 1 over the radius on the other side. I always forget which radius is which. I think for this f, I think this on this side is R1. And this radius in this direction would be R2. So it's related to this ratio. In fact, when you make eyeglasses, that's basically what you do. You start with a piece of plastic, and you basically put 2 radii. One spherical surface on the inside, one spherical surface on the outside, or a toroid if it needs to be for astigmatism. But the simplest relationship with something like this.
So, but then what I'm trying to wrap my head around is, if you don't have a spherical shape, then where is the radius measured from?
If you don't have a spherical shape,
the maximum radius?
It's a radius of curvature. Oh, if it's a parabola, it's a you can't use this expression anyway.
That's my point. That's my point. So it has to be.
You have to use foci with a parabola.
Yeah, and that would be the same as the focal distance. The focus of a parabola is where the.
Ironically, yes.
Which I feel like I studied maybe in like 9th grade and
Same
I
here.
remember.
Same here for a long time.
All right.
So there is a relationship because as incident light comes in, its transmission based on its angle relative to the normal surface of the lens at that particular point will determine how it's bent outward. And then the same is true on the opposing surface. So yeah, there's a lot of considerations, but usually what it comes down to is the relationship between the 2 radii. And if you've got an outer surface that's steeper than an inner surface, you're going to have a plus lens. So that would imply this would be R2, and this would be R1. Or I guess it might be something like that. They never bulge outward on both sides.
On glasses, no.
On glasses. And if it were a diverging lens, it would be flatter on one side, on the outside than the inside, as light's passing through. But it depends on the ratio of these two radii. I forget, I have to even plug a number in and check the calculation and remember which way it's for, so I just forget off the top of my head. But it all reduces if we physically make the measurement, or we're just sort of starting with an accepted value with knowing something about it. However the lens is produced to get there. Okay. And we're getting ready. So let me just do a quick, no, we'll come back to it first. Rather than trying to cram 20 minutes into 5. I will say this though. If you take an object and bring it really, really close inside the focal length of a converging lens, it will not produce an image on this side. It will produce an image on this side. And that image will be larger. And we would say, oh, this sounds like a magnifying glass. A magnifying glass is essentially a converging lens. But we look like this instead of out here, like this. So we get an enlarged, instead of an inverted, we get an enlarged upright image, but it's not real. As you look through the lens from this side, oh, I see my reading, my newspaper over here. You never actually see it over here. Bizarre. Most of the things that we see are not real images, they're actually virtual images. At least when we wear eyeglasses. Okay, go, 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 go. Enjoy the rain and have a great afternoon. And we'll extend this.
Makes you wonder.
Well, if I could have just started with 2 lens systems, not knowing exactly what happened on Thursday, I didn't.
What about over there? Like, what about the magnification? That's the real world. Yeah, that's based on the observer. So, this shit, I can't pay attention because I'm always like just wandering off on like some other tangent. Like, yeah, okay, all right, class. Let's turn this off here.